Okay, welcome back to Evil Dojo. This is part 3 of the entity component system in C++ series. I'm Dark Mage. You can check out the source code for this at github.com/mikedesu/ECS. I want to give a big thanks to everyone who's watched the previous videos. And if you enjoy this kind of material, please like and subscribe and share with all your friends. Anyone who's interested in learning some computer science and shit from scratch, I'm very interested in teaching and presenting materials and doing cool shit with the hope of actually making a real full-blown game out of this project by the end of the whole deal. Anyone who's come here for the dog videos, I appreciate the support. You'll see a lot more of those going forward as I just, really enjoy hanging out with them when I'm not here at the computer. So with that in mind, I'm going to show you the current state of the game, and we're going to talk about all of the different changes that I've made since last time, of which there are quite a few. I find that it's probably a little bit easier for me to work by not necessarily recording me coding on the fly, but perhaps going over the code that I've written after doing so. And we're going to kind of experiment with the formats a bit and see what works best for you guys. If you have any suggestions, I read all the comments. I respond to everything that, is response worthy. And yeah, let's get into it. So here we've got a video of the gameplay from the current implementation of the game, which is generically just a ton of eyeballs spawning on the screen and all moving at various velocities on the X towards the left. The player is able to move up, down, left, right, fire knives, which have a nice little spin to them. And you can also move fast using the shift key and holding it down and moving and using any of the arrow directions. Okay, it's time to go over all the changes made since last time. We'll start at the top. I've written out a transcript here I'm going to be kind of using to help guide me along, because there is a lot of material here. The code is significantly longer. It's now sitting at 758 lines as of April 4th at 9:09 Central Standard Time. And one goal I have is to try and keep the code base beneath a certain line count. What that line count is, I've yet to determine, but I do have a rough idea of when that'll be. It'll be when the engine has reached a satisfactory point and contains a number of critical features. Some things that are to come include all of the nice backgrounds and scrolling effects that I had in the original build of the game. Calling it a full-fledged game is a bit of a stretch, but it contained a lot of the moving parts you would expect to find in any game. And we're fast approaching matching the original engine in both what it was able to do and greatly extend our ability to add new features easily. All right, enough blabbering. We got a ton of different uses and includes. I actually didn't make notes on them, but it's very clear what they all do, generally speaking. I like to use this sort of notation rather than actually putting the std : into every line that uses it, because it ultimately reduces the amount that I have to type. Plus, this is a good way to be very explicit about what methods or functions you happen to be using from the standard template library. See, at the very top, we define a entity type. We define an entity ID type, which may or may not have been in the previous code base. But we prepare for enemies by declaring an enemy type, because we already have an eyeball on the screen. And it's going to be used later in an invisible entity called a generator. I've created a new component to describe a generator right here, which takes a enemy type, a timer, which is currently unused, and a cooldown. Timer's probably going to eventually go away because I don't think we actually need it. The original thought there was to actually decrement a timer and compare it against its cooldown, kind of like how I'm doing with knives at the moment, which I will show you soon. We prepare for a collision component, and we do this by declaring a collision pair. We also have a rotation pair. I don't know if this was present in the previous video. I don't think it was, but we now have the ability to actually rotate our sprites as well as do collision detection. Here's a big list of the declarations of methods, or rather functions, that we're using. A method belongs to an object, and we're currently not really using objects, so to speak. No classes like that. But each one of them is organized by return type as well as alphabetically, or mostly alphabetically. But this is the essential, full set of functions that we're using to work with the game, and anytime that we need to add anything new, it's going to go here first, so that way we don't have to worry about the order that things are actually defined in later. This is a common practice in C and C++ programming. All right, so a lot of the functionality in the previous videos has been refactored into actual functions so that we're not shoving everything inside of the main. This allows us to encapsulate repeatedly used chunks of code into callable functions and give them English-like names, like generate random char, init target texture, clean up and exit with failure, update transform components, handle key up, key down, load debug text, load knife sheet texture, render sprites, etc. This is generally standard and good practice for any programmer, coder, or software developer of any level of the stack. Learning about how to refactor code into functions is a standard part of any good computer science course. It is also a great way to alleviate yourself from downward code pressure. There's a great article by Visual Studio Magazine that I will link in the video description about the negative effects of tools like GitHub Copilot on code quality. And while I use Copilot myself, I make a great effort to not only check what it produces, but also to move the code into an appropriate location once I've confirmed that it works as intended. We have a lot of global variables. So starting from the top here and going down, this is generally considered bad practice, and if possible, I'd want to technically move these things into the main function, but the problem with that is that a lot of the existing functions have been written in such a way as to rely upon the global variables. So if I were to do that, I'd end up having to rewrite a lot of these functions to accept references to parameters that would be declared in the main function. Because the game's not being written to be multi-threaded, I may not necessarily have to worry about this. A lot of game engines use global variables as a standard practice, despite it widely being understood that global variables are considered bad practice in software development. Please give me your thoughts about global variables in the comments below, and whether or not it is more performant to have everything declared on the stack versus the heap. Because in the end, everything is going to have to make some sort of address calculation to access variables anyway. So does it make more sense to refactor all of the functions to use references instead? Would exploding the parameter list for the existing functions result in any negative performance for the game in general? These are kinds of questions and thoughts that I have going forward as I work through this. Let's see, we introduce a RNG generator and a uniform real distribution that will use this RNG generator to create a very nice random distribution of float variables we'll use for the eyeballs x velocity. Let's see. Okay, so now something fun. Just like in the previous engine, I'm introducing a series of Lambda functions that are used in later functions in order to update large numbers of entities that might exist in a map, or a large number of entries. So as an example of this, we have a draw sprite Lambda function that takes a sprite pair, which is defined as a entity ID as well as a sprite component. So the sprite pair gets passed in on every iteration through a for each loop, And all we end up actually doing is calling render copy x, which allows us to pass in the renderer, the texture from the sprite pair, the source rectangle, the destination rectangle, the angle from the transform, a point at which the sprite is rendered around, and then also whether or not the sprite is flipped. So eventually we're going to have to attach like a flip component to our sprite or a transform in order to actually be able to flip our sprites. Similarly, we also have an update animation that does something similar. It takes a sprite pair, and whether or not the sprite is animating, we go through and we update the current clip on that sprite, which allows us to update the source X component, which points to where on the texture we're actually getting our rectangle from. This gives the appearance of animation by moving that frame sitting on top of the texture over an equivalent amount for the number of different clips in that texture. Think of it like kind of like a little animation sheet where each frame of the animation is stored right next to each other, and so we're kind of moving like a camera on top of that image, moving it over. Handle transform does something similar. It goes over our list of transform components. For each one, we go through and we grab the various pieces from it, like the X and Y location, and then we actually copy these values over into the sprite's destination XY. This might be an extraneous step, but it's working out right now. And so long as the ID of that entity is not equal to the player ID, and it is an enemy, because it has an entity or is enemy component, then we check to see if we need to mark it for deletion. Because if it has moved to the left of the screen a sufficient distance, then we want to actually remove it from our game. So that'll actually get handled later. If it is marked, then we can increment a value called number of enemies escaped. Otherwise, if it's a knife, then we want to mark it for deletion only if it's gone far enough to the right of the window, because the skull is flying from left to right, and so are the knives. And if a knife manages to make it all the way outside, then we don't really need it anymore. It's gone forever. And so we want to actually delete it so we clean up our memory properly. And last Lambda function is handle rotation, which also similarly uses a rotation pair. This is how we can define whether or not a sprite needs to be rotating. Because there will be cases where, like, for instance, by default, the knives are rotating when you fire them. And eventually we're going to play around with making the angle of, or the speed of rotation dynamic, so that some knives are rotating faster than others, and other enemies and objects might also be rotating for one reason or another. So this is something we definitely want, and anytime that we need to do any sort of like unique transformations on individual sprites, we can mark them and add a new component to our system in order to achieve that. So the main is so clean that it can fit on the entire screen, and I'd like to keep it this way. It was a real exercise for me to move everything into appropriately named functions, but it's also varies in practice, and it can be quite boring for other people to watch. And honestly, this is what took most of the time for me to do off camera. I did not want to make my viewers suffer through that. So if you were looking forward to some refactoring content, I'm very sorry. You're just going to have to wait for me to make that. I want the meat and potatoes of the series to be focused on good, clean coding and feature development. So we have a number of init functions that we run through. Init RNG, SDL init, create window, render, set render draw mode. Actually, that can, I think we already have that somewhere, but so that might be a duplicate line. But we also init the image library. We init TTF. We init our target texture, skull sheet, eyeball sheet, knife sheet, the global font, debug text panel and rectangles, target texture rectangles. And we actually spawn the skull and the generator for the eyeballs. And now we have our game loop, which does the following. We handle input, which reads input events from SDL, and it passes those to the input components. We then update our transform components as well as our animations, rotations, knife collisions, and generators. Finally, we render our frame. We update the knife cooldown. We clean up any entities marked for deletion on every frame. And then once we're ready to actually exit the game, we clean up all of the textures and various associated maps, and we exit with success. Update generators, first function in our implementations here. So these are not presented in any specific order other than the order that they're defined in, because so long as you declare your functions up at the top of the program, you don't have to worry about the order that you define them in. Update generators is very straightforward, just like all of the update functions. For every key value pair in our generators map, we grab the ID off the first part of the pair and the generator off of the second. And we check the cooldown on the generator. If the current frame count is a modulus of the generator, or some sort of multiple, then we can go and check the generator type and handle it appropriately. This is also where any new defined enemies that we want to use in a generator will go. So update knife collisions is a double loop, so it's a little bit more involved, but for a given item in the isKnife map, we grab the ID and the sprite associated with that knife. Then we also go through our enemy list and do something similar where we grab its ID and its sprite component. And if it's not an enemy, then we skip it, and there's really no reason for this. But for some reason, the knife was colliding with the skull, and I hadn't set it as an enemy, so we just double check to make sure that we're not attacking the player. Actually, this might be something that we can optimize a bit. But then Copilot geniusly figured out, and I didn't realize till the other day, that SDL has a intersection method. This takes two rectangle references, which we pass our knife and our enemy into, and if they intersect, then we mark both of them for deletion, and then we increment our number of collisions. Very straightforward. Next, we have cleanup entities marked for deletion, which goes through our isMarkForDeletion map, grabs the ID for every entry, and if the second value, which is a Boolean, is true, then we go ahead and erase that particular ID from all of our different component maps. We also keep track of the marked for deletion IDs, because attempting to erase them inside of this loop is going to result in a program crash. You cannot update a map or data structure that you're doing this sort of loop on top of, and this is true in many other programming languages. There's ways to do it where you can iterate over a list using indices and then delete a particular index from that map or vector or whatever data structure, but this is another way to do it as well. So once we actually go through and we delete all of the associated key value pairs from our maps, we then go through the IDs that actually were deleted and remove them from our isMarkForDeletion. And then we actually clear those temporary entities from our vector, and then that's the end of the cleanup process for every frame. Load debug text takes snprintf and generates a very big item that sits inside of our texture text buffer. This contains all of the different values and variables that we want to track in our debug panel. It's a very expensive operation to do on every frame, but for debugging purposes ends up working out very nicely. Next, we go ahead and create a text surface using TTF render text blended wrapped, which returns a STL surface. We pass in the font, the texture text, the text color, and then a wrap length so that line wrapping actually occurs. If the surface returned is null, then this is an error and we print out an error. Otherwise, we can, on every time that we need to load the text or prepare the debug texture, we first check to see if it's null, and if it's not null, that means once it's previously created, we go and destroy that texture and set it to null. Once we've done that, then We can go ahead and create a new texture from the previously created surface, check if it's an error, and if it's not an error, we go ahead and grab the text surface width and height, and then we free the previous surface. By grabbing the width and height, we know pretty much how wide and how tall to make our debug panel when we actually create it. Get next entity ID is very straightforward. We have a global next entity ID that's an entity ID type. We increment it and return the previously, the previous value. Or rather, return the previous value, then increment. Distance is currently not being used yet, but I have it in here in preparation for a time when we actually will need to use various geometric and trigonometric functions. Frame time's also not being used, but was previously being displayed in the debug panel in order to display the actual render time for an individual frame. What ends up being more useful, though, is FPS, which is defined as the frame count divided by SDL get tick 64 divided by 1000. Now it's time for spawn eyeball. So this is called by the generator, and we're going to have to get to a point where we can make the process of adding in new enemies and eyeballs and sprites a bit more easy, because at the moment I'm having to hard code a few values in, such as the key used to actually load it from our textures map, the number of clips, whether or not it's animating. We have a generic way to actually get the width of a particular texture based off of the number of clips. So all we have to do is take the texture that we read in, divide it by the number of clips, and that's the width of each individual clip. We get a new ID, and then we generate some random XY values. Well, XY, so the X isn't really random. This is the far right side of the screen, but the Y that we generate is a random value modded by the target texture height minus the height of the individual sprite. That way, when it if it spawns towards the bottom, it's not off screen. It's currently not having a VY, so there's no up-down movement because I haven't implemented bouncing on the sides of the screen yet, but the VX is defined as a distribution from -4 to 0, so that way we get a wide range of different speeds for all of our different eyeballs we generate. Then we need to specify an angle, and then creating the actual component for the sprite is this easy as just creating a big struct and then copying it into the sprites map. Same thing for transforms. Is collidables just a Boolean? Is enemies just a Boolean? And then we push the ID back onto our entities vector. Similar process for spawn knife, except at the very beginning we check to see if the cooldown for the knife is 0, because if it's not, we don't want to create a knife. This can result in too many knives being on screen, but over time I eventually plan to introduce power-ups that will lower the knife cooldown and allow you to fire knives faster. Handle key down. So the way that key down is actually handled, let's see. Yeah, handle key up and key down. So handle key down is actually called by handle input later on, but it receives an SDL key event, and we switch on the particular symbol that's returned by that event. If it's a key down event and it's any one of these different keys, then we update our isPressed map to have true for that value. Otherwise, if it's Q, then we actually set quit to true, which will allow us to quit and clean up the program. If it's D, that allows us to turn our debug panel on and off. So it's depending on the value of the Boolean, it'll render. So the reason that we actually do isPressed using a map and Boolean values instead of just directly updating or handling the events themselves here is that for one reason or another, and this is something I can only muse on, for instance, if we were to have the skull's XY movement handled directly in here on case, SDLK up and down, what ends up happening is a very choppy kind of movement where the initial press jerks a little bit, and then there's like a kind of a couple frame pause before like the movement continues. and then it's kind of a bit stuttery after that. However, doing it this way, we can actually achieve very smooth, buttery smooth sprite movement. It feels like as soon as you push the button, like left, right, up, down, sprite immediately responds and there's no input lag, and it feels very nice. So that was something I kind of like discovered on my own, just playing around with trying to make it work better. Similarly, handle key up just hits is pressed and sets it to false depending on what key event we actually send it. And then of course handle event polls SDL poll event to see what input, if any, the user has done on this frame, and then we appropriately handle it if it's a key up or key down event. Okay, next we got init target texture, which takes the SDL create texture function and actually generates what is essentially where every frame gets painted to first before actually getting copied to the screen. What this allows me to do is actually play around with zoom values and resize the size of the surface that we're actually drawing to, so that we can make sprites and the scene in general as big or as small as we want, which is a really nice thing in the long term, because there are definitely plans for levels that, you know, the perspective is set further away from the skull and some might be closer up, and we get to play around with that kind of stuff as a result of this setup. Cleanup textures is just a loop that goes through the textures map and destroys each of the texture pointers, which we need to do in order to properly free up all of our memory, and then at the very end actually freeze every item in the textures map. The full cleanup method calls all of our different various clear methods for the maps and cleans up our textures, then destroys the debug texture, the background texture, the target texture, and then it destroys the renderer and the window, closes the font, and then closes each of the different libraries. Init debug texture rect, init target texture rect, very straightforward, just goes through and sets some values on our default rectangles for those entities. We clean up and exit with failure, which does exactly what it says it does. Calls cleanup, exits with failure. Clean up and exit failure imprint does the same thing, but it uses my imprint code, which I could just show a little bit of that off too. Imprint is a defined macro for cout, could also be used for printf, but it essentially gives us the date, the time, the file, and the line number, which is really cool, of the the various location where the line gets printed, which ends up being extremely useful and makes printf style debugging like on crack. So we actually use that function in our various create window and renderer methods in order to handle the errors. So if we actually encounter an error in either of those, we call cleanup and exit with failure imprint, so that we know not only where in our program the failure occurred, but also exactly what happened. So always try to handle your errors and give good feedback and output, so that you can very quickly identify what may have gone wrong if your program happens to crash. I know people are trying to write crash-free programs, but you should definitely consider that your program might crash along the way. So code defensively. Init TTF, init IMG essentially does the same idea, except they load up the libraries. Init gfont loads the font. We're currently hard coding that in. Hack is a very good font. It's also the font that I'm using for the source code here. Also a font that I've been using for like the last 13 years or something like that. It's a long time to be using any font, but I mean, if it works, don't fix it necessarily. I've tried other fonts, but there's something about it that really hits. All right, handle init target texture. It's just a wrapper to init target texture and just some error checking, and handles it appropriately if it fails. Load target texture loads the skull sheets texture. Sorry, load skull sheet texture. And if it loads successfully, then we assign it to the textures map for that key. And that way we can very quickly access textures that we've loaded in for one reason or another. I want to build a system that makes this process a bit easier so it's not so hard coded, right? Like I want to have like a config file where I can specify all of the different textures as well as their associated like number of clips for the animation in a file, and then be able to like load that from a file. I think that's a really good goal for this project, because ultimately we would be able to separate out the loading of the textures from the source code and also be able to more easily add in new textures whenever we need to, because at the moment this is highly suboptimal. It works and it's towards the direction of optimal, but we have to smooth this process over somehow. And the only way that I can think of off the top is going to be by writing some sort of configuration file system. Similarly, for a load knife sheet texture, we also hard code in the position of the knife, and then we load the texture. And then if it errors, we clean up and exit, and then we also assign that texture to the knife key value. The actual function to spawn skull, and similarly, I want to smooth this process out, right? Like this loads the, this actually instantiates the skull on the screen. So it pulls from textures when it does SDL query texture in order to get and calculate the number of clips that exist on it. So we're actually kind of separating out the loading of the texture from the like generation of the sprite itself, which is probably a good thing. But we have to be sure that whenever we're creating a new thing on screen, that we do all of these steps beforehand. And if we can find a way to smooth that process out, we definitely want to. But in other words, we define a bunch of values, and then once those values are ready and we have like an ID for the entity, we just add that sprite to our sprite component list, or our map. Just a big struct with predefined values. And then we do the same thing for transforms. We set the inputs ID to true. And honestly, I think I have it set up so that there can only be one entity in the inputs map, which there's probably another way to go about handling this, but it makes it very straightforward. I was going to do something similar with the player ID, but at the moment I'm just kind of using a variable for that. And then we push that ID back into the entities vector. Now it's time to handle the input component. Let me get a sip of coffee before I continue. I said a sip. I took 4 gulps. All right, for each key value pair in our inputs map, we grab the ID, we grab the associated transform component, and we grab the associated sprite component. And then we handle whether or not left, right, or left and shift and right and shift are pressed, because those are 2 different states. We want to check to see if shift is pressed first, because otherwise, if you did these in the other order, the if statement for is pressed left would actually trigger before the check for the shift key. So you need to do both at the same time first. This is generally good practice for when writing if statements or branches in general. You want to be aware of which branch is going to be taken first. And so if we were pressing the left key down to like move left, and we had the second set of if statements here above the first set, then the check for if left is pressed would occur before the check to see if left and shift is pressed. And you could even rewrite this, but I like having pretty not nested if statements if possible. There's a lot of benefit both in readability and like performance in general to just keeping things really simple. So we check to see if left and shift are pressed, and if they are, then we can move by 8. And this is also something that I don't really want to hard code, but I'm doing so at the moment. More on that later. But basically, if you're moving fast or running, you move by 8 pixels per frame. And if you are moving normally, you're only moving by 4 pixels per frame. In the original zooming, in the previous implementation, when everything was just 1x, this value is 1. But because everything has been scaled up by 4x, the initial movement speed is now 4. And I think this is a good basis. It feels exactly the same as it did when it was a quarter of the resolution. So we have a 1-to-1 there. And the whole reason I ended up zooming in, you know, in other words, stretching, I don't know, I need to turn my phone off. The whole reason that we zoomed in was that I found when I began applying rotations to the knives, that the knives were not rendering smoothly. I can go back and do video on that, but essentially attempting to do the target texture at like a quarter of the current size and then stretching at 4x resulted in the knives getting stretched sufficiently that when they rotated, there was heavy pixelation. And it just didn't look right. It didn't look good. And one of my goals is for it to not only maintain that old school appearance, but to actually look and feel good. And honestly, it didn't feel good. So, you know, this was a very important step. We separate out handling up and down from left and right because it makes sense to have up and left, up and right, down and left, and down and right pressed all at the same time, but not like up and down or left and right at the same time, right? So we separate those out as two separate if blocks. So this is one if else block, like right here. And then this is also a big if block. So in addition to that, like, you know, not only can you be moving, but you could also have the A key pressed. And if the A key is pressed, we want to spawn a knife. We want to set the sprite current clip for the skull to be 1, which would be its mouse open state. And then we want to update the source X to point to that new current clip. So in order to do that, you take the sprite width, you multiply it by the current clip, and that gives you the X value that you need to put on your source rectangle. So that's essentially how basic animation works, and it extends towards any number of clips too, which is really nice. But at the moment, there's only 2 frames of animation for the skull, and working out like making a better multi-frame animation for that is something I'm kind of tossing around in the back of my head because the little details do matter. And while we might get a very working game in the end, if I can make little details look and feel good along the way, I really want to do that. Once we've assigned all these new values, we can copy the sprite and the transform back over to their respective map location. All right, next up, we've got update transform components. I'm not even using the transcript at this point. So this is something that makes use of a functional programming procedure called for each, which essentially takes a standard template library, begin and end location, and then handles a transform on it, which this is, reminder, a Lambda function. So handle transform, right? This is where that's actually defined. So this gets called down in update transform components using for each. And this is actually functional style programming in C++. So given a constant transform pair T, and a transform pair again is an entity ID paired with a transform component. So when you iterate through the transform map, which is an unordered map, you get back the key value pair for each like entry in that data structure. So essentially this enables us to like iterate over it, and we can actually run this function on each iteration. You could be like, why not just use for loop, man? You do that in plenty of other locations. Why not just use auto? Well, I was really interested in kind of testing this out to see like how performant it is and how good it is. And I'd like to do testing to be able to compare this way of doing things with another. So trying it out and making sure that you understand the syntax and kind of essentially what it is that you're even implementing to begin with. When you have an idea, just try it, you know, like there's no harm in it. This is the first time I ever did this and it worked pretty good. I feel like I have an idea for a general pattern of doing it and it feels right. So yeah. The for each comes from, I believe, functional. So similarly, render sprites also does the same thing, except it's using draw sprite. So draw sprite is defined up here. We've got a sprite pair, which is a entity ID and a sprite component. And all we have to do is one line of code here. It's SDL render copy X and pass in the various values to it. So we get the, we take the renderer, we take the texture, we take the source rectangle, the destination rectangle, the transform angle, a central point around which the sprite is supposed to be rendered, which in this case, because null is being passed in, there's no modification or transform done to the source or destination rather. And then we pass in a SDL flip none because the sprites are not to be flipped at the moment. Render debug panel, 4 lines of code. We define black at half transparency. We set the draw color to that color. We fill that rectangle, that debug texture destination rectangle, with that color. And then we copy over the debug texture, which contains all of the text information that's to be rendered on this frame. Update animation, just like update transform components and render sprites, is another functional for each call. That calls update animation, which update animation is right here. We take the sprite pair again, take the ID, get the sprite component, and check to see if it's animating. And if it is, then we do that update clip that we did to the skull, except to, you know, we're not hard coding in just 2 frames. This actually handles any number of frames. So if you have a strip that's, you know, in this case, eyeballs are like 18 frames long, and comes back, the system's able to automatically figure out how many or how wide each frame of that texture is supposed to be. So update rotations does something similar, except it calls handle rotation, operates off the is rotating map for each rotation pair, which is just like the others, an entity ID as well as a rotation component. Well, the rotation component in this case is Boolean. So if it is rotating, then we grab the transform for that ID, increment it by a currently hard-coded angle, which at some point in the future this will be more dynamic, and then reassign the transform back to the transforms map. And then we call render frame, and this is where like a lot of heavy stuff happens. So we already talked about render sprites, but before that happens, we set the render target to the target texture, and then we clear the screen to be blue. That's where the blue background color comes from. And then we actually call that clear. And we render sprites. And then once we've actually drawn everything to the target texture, we reset the target of the render to like the window. That's what happens when you do render or null. If you do render or target texture, it changes it to whatever texture you pass in. So you can actually draw on top of other textures that you load in. And that's something we should definitely consider playing around with. One of the goals of a previous game that I was working on, Project A iOS, source code available on GitHub. I'd be surprised if anyone's able to still compile it. But what was I going to say? Oh yeah. One of the goals of that project was the ability to be able to draw textures in source code. And using a hack of the Cocos 2D CC texture class, back when I was working in Objective-C, I was able to get pixel by pixel drawing capability, which enabled me to completely throw away the need to manually do my own sprites. I didn't have animation, but it was a work in progress and kind of a proof of concept. And if we can get back to something like that, where I'm able to like add little details in here and there, do stuff like that, I don't know how realistic that's going to be, but it's worth exploring. And in fact, being able to like take some texture, separate it out, that way we could have like dynamic texture. Maybe we can give hats to the skull, you know? Maybe we can decorate the knives when they're being thrown. Something like that. I don't know. But after we reset the target back to the window, we copy that target texture directly to the window using the rectangle we defined. And then we check to see if we need to render the debug panel. If we do, we go ahead and render that debug panel, and then we update the debug panel text as well as the texture. Finally, we're able to present the renderer, and we increment the frame count by 1. We're almost done here. We're at the very end of the code base. Last functions are init.rng, which takes the eyeball VX distribution, which is the generator that we're using to randomly choose between -4.0 and 0.0 to select a random speed for every eyeball that we create. And this ends up having a really cool effect. Last function, spawn generator, and also the newest one. So without following any sort of tutorial, I came up with this on my own, just based off the way that the previous components worked. We go and check to see if the various inputs are good. You know, in other words, we have a valid enemy type, and we have a valid cooldown, but we're not using timer at the moment, and so in the near future we're probably going to delete this from the setup just so that it's more clear, because it's certainly to be confusing to like be watching this video and say, but hey, you have this timer defined up here, why is it even still there? Why didn't you even just take the time to delete it, you know, from before you made the video? And that's because I wanted you to understand that code is dynamic, right? Like nothing is set in stone. And so just because you have something that works here and now doesn't mean that it's not going to change in the near future. So it's really important to understand that coding is not a thing, or code is not a thing, but a doing. How zen of me. Okay, so after we've verified that our inputs are good, for every key value in our generators pair, we also go through to check to see if we already have a generator of that type. And if we do, then we're not going to add it, because at the moment I only want one generator of every type to be present in the game. So that way we're not like managing multiple generators for a given type, you know. It's possible that might change in the future too, but at the moment I don't see a reason for me to have like 2 eyeball generators. That doesn't make sense. It's excessive, unnecessary. Why would I do that when one generator is sufficient? So we get a new entity ID, we construct the struct for that generator, add it to the generator's map, and then add the ID to our entities map. And that's everything up to this point. So this project is a journey, you know, in general, that I've walked the beginnings of countless times at this point, and I'm ready to really push things much, much further. You can tell I'm reading from transcript now again, but just work with me. We really need to smooth a lot of things out, as you can see, such as the process of adding new entities and components. Being able to specify these things in a config file would be really useful. But I am looking forward to this becoming a regular video series. This is part 3, and you know, we're not anywhere near done yet. There's so much more to actually come, and I have to create an ebb and flow between working on the game project and then going back and making these videos where I cover what I've done. And if I can make this like a weekly thing or something like that, I think that's a great goal. It doesn't seem unreasonable given my circumstances. When I'm not here at my computer working on code and doing various projects and helping students out, I'm usually away from the computer. If not playing, with my sister's dogs, then I'm also helping out my grandmother, who is very elderly and requires a lot of care here at home. So if you've enjoyed me running through the existing source code for my game, because honestly, I wouldn't even be a programmer or game developer if not for my grandma, then please like and subscribe and share with all of your friends. I've been teaching, tutoring, blogging, and vlogging for over a decade, and I'm looking forward to doing it for many more years to come. This has been the Dark Mage of Evil Dojo, and we're signing off. Until next time. Take it easy.